Hello, Math 95 students. We are moving on to Chapter 9. Chapter 8 was all about factoring quadratic expressions and then using that kind of a method to solve quadratic equations. But many quadratic equations can't be solved by factoring. And so when that's the case, we need some other ways to be able to solve quadratic equations. One of those ways is going to be the square root method, and the other way is going to be the quadratic formula. All right, so those are going to be the two ways. 9.4 is about the square root method, and 9.6 is about the quadratic formula. 9.3 is something that we need to is kind of a background section. We need to be able to do this right here, simplify radical expressions if we're going to be able to do the square root method and the quadratic formula. So we're going to look at square roots. So let's look at this right here, the principal square roots thing right here. What number squared is equal to 9? Well, there's two numbers that when you square them equal 9, 3 and negative 3. 3 and negative 3. All right? So the square root of a number is the number that you can square to get a. So if you wanted to take, if you had x squared equals 9, then this would be true if x were equal to 3 or if x were equal to negative 3. All right? So now we also have something called the principal square root. The principal square root. The principal square root is the positive one. All right, the non-negative one. So if you just saw this, the square root of 9, then the expected answer here would just be 3, not negative 3. Okay, even though what we just set up here is true, and we'll get into that later. But this is called the principal square root. So if you just have an expression that says the square root of 9 or the square root of 16 or whatever, it just wants you to write the positive one as the answer there. All right. That symbol right there is called the radical sign. The radical sign. The expression under it. So like this right here, the 9 is called the radicand. It's the expression under the radical. All right. Look at the warning right here. The warning is that it says, is the square root of a negative number a real number? So it says, consider the square root of negative 9. What is the square root of negative 9? Well, negative 3, when you square negative 3, you don't get negative 9, you get positive 9. And when you square 3, you don't get negative 9, you get positive 9. So the square root of any negative number is what we call a non-real number, also known as an imaginary number, which we'll get into later in this section. All right, so if you have a negative number under the radical, for right now, you're just going to say that that's not a real answer or not a real number. Later on, we'll talk about how to get an imaginary answer for that. All right, so when we're doing the square root of a number, like let's say the square root of 49 here on number 1, what we're trying to say is what number times itself gives you 49? What number that when you square it gives you 49? All right, well, we can break this down to 7 times 7. And so since a pair of 7s multiplying with each other give you 49, the square root of 49 is 7. So the answer to the first example here is 7. Number 2, the square root of negative 49, because there's a negative under the radical, we're just going to say that that's not real, not a real number. Now number 3, the negative is not under the radical. So the square root of 49 is 7, but there's a negative number that follows it, right? That's on the outside, so the answer to number 3 is negative 7. All right. The answer to number 4, because there's a negative number under the radical, again, means that it's not real. Non-real. All right. Now, as we do these, it's going to help us if we know some of the perfect squares. So, for example, what is 0 squared? 0. What is 1 squared? 1. What is 2 squared? 2. I'm sorry. What is 2 squared? 4. What is 3 squared? 9. Let's keep going. Hopefully you already know these. Do you know these higher ones? 121, 144, 169, 196, 225, 256. It's taking me a minute to think of some of these. 289. I believe it's 324, but let me make sure. I did check that one in my calculator and it was 324. 19 squared, I went ahead and did that one in my calculator, that's 361. And 20 squared is 400. So I think I have them all memorized pretty much except for 19 squared. That's one I can't ever seem to remember for some reason, but it would be good if you were familiar with all of these perfect squares so that you know, you can recognize when, like, let's say you had the square root of 324. It would make it much easier if you know, hey, the square root of that is 18. I don't have to do any work, I just know that. All right, this next example is about approximating square roots. Like figuring out, like if it's not a perfect square root, the square root of 19 is not a perfect square root. But we can kind of estimate it. We can think, well, what is it near? And we can do that by thinking, what are the perfect squares that are near 19? Like what's the nearest perfect square root of 19 that's less than 19? It would be 16, right? The square root of 16 is 4. What's the nearest square root of 19 that's higher than 19? 25. What's the square root of 25? 5. So then the square root of 19 is going to be somewhere between those. We're not going to be exactly sure what they're between, but it's going to be 4 point something. So maybe we say 4.5 or 4.6 or 4.4, somewhere in there. I'm not real sure. So I'm just estimating it. I'm going to put a squiggly equal sign to show that this is an approximated answer. All right. What about number 2, the square root of 169? Well, that is a perfect square. So I don't know if you remember that one, but the square root of 169 is 13. There's also a technique called simplifying radicals. So like the square root of 12 is not a perfect square root, but it is a number that can be simplified under the radical. Let me show you what I mean. So if we take the square root of 12, there's 2 ways we can simplify this. One is by thinking of what is the biggest perfect square that will go into 12. Okay? The biggest perfect square, is there any perfect square? And if so, what is the biggest perfect square that will go into 12? And that would be 4. 4 is a perfect square that will go into 12. So we break the 12 down to a 4 times what times 4 gives you 12 is 3. So a 4 and a 3. And since the 4 is a perfect square, then we bring it out by taking the square root of that number. Take the square root of that 4. All right, square root that number. And that comes out of the radical. Okay, so that will come out as a 2. Whereas this 3 right here it can't do anything, so it must remain under the radical. So 2 times the square root of 3, or some people say 2 on the square root of 3, is how the square root of 12 can simplify, and it's equal to the same exact value. Now there's another way to do this. All right, there's another way to break down the square root like that. So if we're breaking down a square root means something times itself that gives you that number. So we can break the 12 down to what's called its prime factorization. So the 12 can break down in any way you want. Okay, we can break it down to 4 times 3 or 2 times 6. All right, it doesn't matter which way you go. If we say 2 times 6, then the 6 can also break down to 2 times 3. Now, none of these can break down any farther because they're all prime. But now I look for numbers that multiply with themselves. In other words, I look for 2 of a kind, 2 of the same number. And I have a pair. I have 2 2s. I have 2 of a kind. All right, I have a pair of 2s, which means that 2 is multiplying with itself, with that other 2. All right, so that if you find a pair, they come out. That comes out as a 2. So think of it like breaking out of prison. If you have a partner, then the two partners can work together to break out of the jail of the square root symbol. But the 3 does not have a partner. Nothing is like the 3. It doesn't have a partner, so it can't break out of the jail. It has to stay in there. So the 3 stays under the radical. So again, that's another way you can simplify radicals. You can do their prime factorization like we just did, or you can look for the highest perfect square that will divide into that number and break it down that way. So either one, whichever one of those ways makes good sense to you, go with it. Let's do the next one, the square root of 32. All right, I'm going to break it down like this. I'm going to say that's 2 times 16. And 16 is a perfect square. So that's going to equal, the square root of 16 is 4, but the 2 is not a perfect square, so it has to stay under the radical. If you had done it the other way, you could break the 16 down to 2 times 8. And then the 8 down to, I'm going to go this way. The 8 down to 2 times 4, and the 4 down to 2 times 2. So again, I'm looking for 2 of a kind. I got a pair of 2's there. I got a pair of 2's there. I got one extra 2 left over. So this pair of 2's comes out as a 2. This pair of 2's comes out as a 2. That means on the outside I have a couple of 2's out there. They're going to multiply together and get 4. And on the inside I still have that one extra little 2 left over. All right, number 3. We got 7 times the square root of 45. And what we're doing is we're breaking the 45 down. 45 breaks down to 9 times 5. And then so the square root of 9 is 3. So that'll come out. So the 3 comes out and multiplies with the 7. So now I've got 21 on the outside, and that 5 stays underneath the radical. Or if you had done it the other way, the 9 breaks down to 3 times 3. So I got a pair of 3's with an extra 5 left over. So the pair of 3's can come out as a 3. And again, there's the 7 that's already out there. So the 3 comes out there with the 7. And the 3 multiplies with the 7 to get the 21. So that's where that 21 came from, and that extra 5 is left over that has to stay under the radical right there. All right, example 4, simplify the square root of 72. I would encourage you to pause it and go ahead and try to do that on your own before we do it together. So the square root of 72, I think what I would do is I would break that down to maybe 2 times 36, and then the 36 is already a perfect square, so that becomes a 6 on the outside with a 2 on the inside. Or if I could continue to break this down, 36 breaks down to 2 times 18. The 18 breaks down to 2 times 9. The 9 breaks down to 3 times 3. So I'm looking for partners. I have a pair of 3's, I have a pair of 2's, and I have one extra 2 left over. So the 3's come out as a 3, the 2's come out as a 2. So I got a 3 and the 2 on the outside that makes the 6. And then that extra 2 left over that doesn't have a partner is still underneath the radical. Okay, now we're simplifying radical fractions. When you have a fraction, that's underneath a large radical sign that's over the whole fraction, I would encourage you to break that up into 2 separate fractions, a top fraction and a bottom fraction. So the square root of 5 over 9 can break down to the square root of 5 over the square root of 9. So we have a top fraction and a bottom fraction. I'm sorry, a top radical and a bottom radical. So notice that the square root of 9, that's a perfect square. That's just 3. So it's just a 3 on the bottom now, and a square root of 5 on the top, and that's how I simplify that expression. All right, the square root of 50 over 81 is going to be a little bit more involved. I still break it down to a top radical and a bottom radical. All right, notice that the square root of 81 on bottom is a perfect square already. It's going to be a 9. So I'm just going to have a 9 on the bottom. Now on the top, the square root of 50 is not a perfect square root, but I do believe it can break down. Let's see if the 50 can break down. That breaks down to 2 times 25. And the 25 is already a perfect square root. Or if you want to break it down more, it's 5 times 5. So 5 times 5, that means that that's a partner that can come out as a 5. So I've got a 5 on the outside, and notice that the extra 2 is left over, so the 2 is still under the radical. So this is how I can break down that into its simplest form. All right, this next example, we have 5 over the square root of 7. Now the radical is not over the whole fraction, it's just over the bottom part. All right, we don't want to have a radical on the bottom. It's okay to have a radical on the top, but not to have a radical on the bottom. So we must do something to make the radical on the bottom go away. That's a process called rationalizing the denominator. Rationalizing the bottom, which is called the denominator. The best way, usually, to do this is when you have a radical on the bottom, the best way to make that radical go away is to multiply that radical with itself. And as long as you do the same thing to the top as you do to the bottom, then you're not changing the value of the fraction, so that's okay to do that. So I've got the square root of 7 times the square root of 7 on the bottom. Now the square root of 7 times the square root of 7, okay, the square root of 7 times the square root of 7 is the square root of 49. And we know that the square root of 49 is just 7. So I've just got a 7 on the bottom, and on the top I've just got 5 times the square root of 7. So this is the simplified answer. This is the simplified answer to that problem. I just want you to recognize something. When we multiply the square root of something, the square root of 7 times the square root of 7, we just get 7, right? So that happens anytime. If you do like the square root of star times the square root of star, you're going to get star, right? The square root of y times the square root of y is what? It is y. That's going to happen every time. So that'll give you a little shortcut. Number 2, 7 over the square root of 18. The first thing we need to do, which we couldn't do in the first one, is we need to simplify the radical. Like the first one, the square root of 7 won't simplify any more than it already is, but the square root of 18 will. So I've got to break that 18 down. It's going to be 2 times 9, and notice 9 is already a perfect square root, so I bring the 3 out. If I want to go ahead, keep going, it's a pair of 3's right there. So this becomes 7 over 3 root 2, right? The 3 comes out, the 2 is left underneath the radical. Now I still have a radical on bottom, so to get rid of that radical, I multiply it with itself. Multiply the square root of 2 with another square root of 2, and as long as I do the same thing on the top that I did on the bottom, then I'm good. So that gives me, on top, 7 root 2. And on bottom, what's the square root of 2 times the square root of 2? It is 2. So I've got a 3, and I've got a 2, because the square root of 2 times the square root of 2 is 2. So on the bottom, I've got 3 times 2. So now I've got 7 square root 2 on top, and I've got 6 on bottom. And that's the simplified version of that one. All right, example 7. Here again we have a big radical over that whole fraction, so we break it up. I'm going to break it up into the square root of 7 over the square root of 3. Okay, I don't want to have the radical on bottom, so I multiply it with itself. Square root of 3 times the square root of 3. And I do the same thing on top that I did to the bottom. So on the top, I've got the square root of 7 times the square root of 3, and that will combine together into a single radical, which is the square root of 21. All right, and the square root of 3 times the square root of 3 is the square root of 9, which is just 3. Okay, so the square root of 21 over 3. You cannot reduce the 21 and the 3 because the 21 is under a radical and the 3 is not. If the 21 was not under a radical, you could reduce the 21 with a 3, but you can't do it when when one of the numbers is under the radical and when the other one is not. You can't reduce it like that. All right, number 2. We're going to break it up into the square root of 3 over the square root of 20. Now what I'll do first is I'll break down the square root of 20. That's going to be 2 times 10, 2 times 5, and the 5 won't break down any. So I got a pair of 2's with an extra 5 left over to go under the radical. So that gives me the square root of 3 over 2 square root 5. Okay, and I got to get rid of the square root of 5, so I multiply it with itself. Do the same thing to the top that I did to the bottom. So that gives me on top, the square root of 3 times the square root of 5 is square root 15. And on bottom, I've got 2. And the square root of 5 times the square root of 5 is what? It's 5. So I've got the square root of 15 over 2 times 5, which is 10. So that's my answer to that one. Again, you can't reduce the 15 with the 10 because the 15 is under the radical and the 10 is not. All right, here we're told to simplify this radical quotient. Okay, we're simplifying this expression here. So 6 plus 3 root 2 over 12. Okay, I want you to think about that this is a term, this is a term, and this is a term. Okay, and all 3 of those terms can all divide by a number that is the same number. All right, we cannot touch what's under the radical. All right, that 2 can't be touched, but the 6, the 3, and the 12, if they can all divide by the same number, they can all reduce by dividing by that same number. Okay, so we're going to divide each one of these by what will divide evenly. What's the biggest number that will divide evenly into each of those numbers? 3. So I'm going to divide them all by 3. And my answer now will be, what's 6 divided by 3? It's going to be 2. 3 divided by 3 is 1. So I can put a 1, or I can just leave the 1. You know, it's an understood 1 that's going to be in front anyway. So I've got just 1 on the square root of 2, or just the square root of 2, over 12 divided by 3 is 4. That's my simplified answer. I cannot reduce it anymore because I can't touch that 2, right? All the terms have to be divisible by the same number. So I can't divide that term because it's under the radical. So I can't divide all 3 terms by the same number. So this is the simplest. This is the term that is simplified. And I can't simplify it any more than that. Example 9. We're told to simplify this expression. So we've got 8 minus the square root of 28 over 10. Right now I can't do anything because I can't touch the 28 that's under the radical. And since I can't divide all 3 terms by the same thing because the 28 I can't touch it at all, then I can't simplify it yet. But what I can do, maybe the 28 will break down and I can bring something outside of that radical that will reduce with the other 2 numbers. Let's break the 28 down. So the square root of 28 will break down to, let's say, 2 times 14. 14 is 2 times 7, so I got a pair of 2's with an extra 7 left over. So that's going to become 8 minus the 2 comes out, the 7 stays under, over 10. Now, all 3 of these terms can divide by the same number. What can they divide by? They can all divide by 2. Divide by 2, divide by 2, divide by 2. So now my answer is 4 minus 1 square root 7, or just square root 7 over 5. And that's my answer to that. And that finishes up all the examples for section 9.3. Good luck on that assignment. I'll see you again in 9.4.